Pearson product moment correlation coefficient. They should have really come up with an easy to read acronym with this. I don't know if that's any better. And of course, if you look at all those letters, PPMCC, it makes sense that you're going to call that an R value. Because if you add up all those letters and divide by 5, you get R. So, not only now, our least squares regression finds us the line of best fit, the best line of best fit for a set of data. Now we need to decide how good is that line for determining things. Is that line really close to our data points? Or is that line not very close to our data points? And this correlation coefficient is going to tell us that. Because if we get an R value that is very close to 1, it's going to tell us that our line of best fit is very close to our data points. It's also going to tell us that our line of best fit is positive and going up. Now, depending on the program that you're using, sometimes they're going to give you an R value, sometimes they're going to give you an R squared value. So this one that's drawn for you here has an R squared value. So our R value is always going to be a value between -1 and 1. A 0, if you get an R value of 0, that means that there is no correlation at all. Your scatter plots are all over the place, and it can't make a line of best fit. A number closer to 1 means that the correlation is strong and positive. And positive means that your line is going up like a positive slope. A number closer to -1 means that the correlation is strong and negative, meaning that your line goes down from left to right. It has a negative slope, but it's still a very good line of best fit. Different scatter plots and different correlation values. You can see that if you drew a line of best fit through this first one, all the data points would be relatively close to that line of best fit. So we have an R value that's very close to -1. The second one, those points are more spread out. We still have a negative slope. Our line of best fit would still have a negative slope, but its correlation is not as strong, and we got -0.5. And finally, that last one is all over the place, would have no correlation. Here we have some positive slopes, and if all of your data lines up perfectly in a line, that's when you're going to get your correlation coefficient to be 1. So some generalizations. Between 0 and 0.25, that's very weak. 0.25 to 0.5 would be weak. 0.5 to 0.75 is moderate, and over 0.75, we would say that that has a strong correlation. So when people are doing statistics and they're coming up with a model that they're saying, this is what my data is saying, and this is my line of best fit, what they'll go is they'll look at their correlation coefficient and say, since my correlation coefficient is 0.95, I'm confident that my line of best fit can be used to interpolate and extrapolate. But if my line of best fit doesn't have a strong correlation coefficient, then I'm not going to be able to say much about this, and I'm not going to be very convincing when I say, oh, I'm going to use this to figure out some information. So you've wondered, how do I calculate this by hand? Well, since we already had those nice formulas, the SXY, we used that already in our least squares regression line. And now we're going to look at SX and SY, which is similar to what we used in our regression line. SX, we used SX squared before. So now you would square root that. And SY would be similar formula. And that would be in a square root as well. Has anyone checked if these formulas are in your formula sheet? They're not. Oh man, does that mean we'll have to use our calculator to find them? But it is nice to know where they come from. So we will use our calculator to find them, but we'll do one example here. The same one that we had from before, and calculate it. And then we're going to look at our calculator to figure out the same thing. So we had this chart from before. I'm adding a y squared column now because we didn't have that from before. We could calculate each of those things separately, plug it into our formula, and we have an R value of 0.5. Now you have this data still in your calculator, right? So some of you, did any of you when your equation come up, did you have R values when you typed it in? Did anybody's calculator have R values already? If it didn't, you have to do something once. And once you've done it once, you will always get your R values. So you're going to go to your catalog. And your catalog button is right above 0. So go second catalog. Now, when you go to your catalog button, the catalog has every single function your calculator can do. You can scroll down forever until you find it, or you can also use your alpha buttons. So here, let me just see if this works. Go alpha D, and it will go to the D, and then you can look there. So when I go to second catalog, it lists everything. If I go alpha D, nothing happened. I need a software update. Let's close that. Let's see. Alpha D. There. If you go alpha D, it goes to your D values. Then you still have to scroll a little bit until you can find your diagnostic on. Push enter on that. Push it once, and it will be turned on. Now, when you go to type in your line of best fit, of course, this is my equation that I have from our second set of data. Okay, if anybody wants to re-put in those 3 points from our first set of data, we can see if the R value comes out to 0.5, like we calculated. But the one that we had from before, the R value is 0.79, so we could say this has a strong positive correlation. Not super, super strong, because it's almost at that 0.75 range,